So first of all, if we go back to the past, in the beginning of the 90s, when I initiated my search of the gene for diabetes, the situation was very simple. Diabetes was considered to be a consequence of insulin resistance, and the pancreatic defect were totally denied or only considered to be a very late event. And there was a popular concept at that time, that still exists, the concept of pancreatic exhaustion, like your pancreas is tired to face obesity. And now we know that it's probably totally wrong, and that patient or subject who will develop diabetes have probably a primary pancreatic defect. And when they are exposed to obesity, inflammatory syndrome, bad diet, and lack of exercise, then the demand of insulin increases, and there might be some also adverse effect on the pancreas, but that leads to a chronic hyperglycemia. And I have to say that this evidence that pancreatic defect are crucially linked to the risk for diabetes is mainly based on the genetic discovery. Immodestly, I can say that maybe the onset of this kind of revolution, the concept, was in 1992 with the discovery that mutation in the enzyme glucokinase, which is the specific exokinase of the pancreatic beta cell and the adipocyte. So mutation in glucokinase were indeed responsible for a kind of a form of diabetes occurring very early in age, named MODY. And we learned for the first time that glucokinase is a glucose sensor on the beta cell, but also the hepatocyte. That means that glucokinase control glucose metabolism in the pancreatic beta cell, which generate energy and is responsible for insulin secretion in response to a rise in glucose values. And in the hepatocyte also, glucokinase is crucially important for the storage of glucose in glycogen. And it was the first time that people accepted the idea that possibly type 2 diabetes might be a primary beta cell disease. So the consequences of this discovery, I think, were important, and one classical thing, or not classical, but one striking thing is the fact that now there's different drug companies that are developing allosteric activator of glucokinase, and that is based on what I showed you just before, that the crucial role of glucokinase in the beta cell and the liver, and also I remember in 1992 when I went to see a drug company and say, you should develop activator of glucokinase. They say, you are totally mad. It's impossible to do this kind of thing. But the drug company, what I've done is I've analyzed very carefully the mutation that we and others found in the glucokinase molecule. And then it's how they develop this activator. So it's a very good example of how genetic discoveries have really helped industry to develop a specific compound that may be a new treatment for type 2 diabetes. And now this compound in clinical development phase 2 and 3. The second consequence of that was the interest of academia and funding bodies in diabetes and diabetes research and genetics. So despite the fact that in 1990 my first grant application on glucokinase was badly rejected by the French diabetologist, later on it was possible to work on that, and a few years later my group found a linkage, chromosome 12, and then eventually in collaboration with my good friend Graham Bell in Chicago, we identified transcription factors in the beta cell as other causes of monogenic type 2 diabetes. And now what we know is that there is a network of transcription factors and that are linked together. And as you can see here, they have about the same target, and these targets also are glucokinase, insulin, and are crucially important for the response of beta cell to high glucose. And what we learn from this kind of basic discovery is two things. First of all, that all these transcription factors are closely linked, which means something important. That means that a mutation in one of these genes is responsible for the same kind of phenotype that a mutation in another of these transcription factors. And the second thing, as there is a co-activation of this transcription factor, if you have a modest mutation in one of these transcription factors, you have a kind of amplification, which explains that after some years, there is a destruction of the function or a profound impairment of the function of the beta cell, and then you have the development of diabetes occurring after some years of life. So these transcription factors are crucially important for the function of the beta cell, but they are also crucially important for the development of the pancreas and the differentiation of the mature beta cell. And that also has crucial implication for people who are doing islet transplantation and try to develop a way to replace pancreatic islet and beta cell that are destroyed in type 1 diabetes, but also in type 2 diabetes. Another interesting thing is that it has been possible to differentiate some, based on genetic testing, some very specific part of highly familial form of type 2 diabetes, and you have some definition here, which is important because you can analyze families, you can possibly prevent to have an early detection and better treatment of these people, especially because this form of diabetes is very severe with a high risk of kidney disease and also ocular diseases. Another really interesting thing is, for instance, for people who have mutation in the transcription factor HNF1 alpha, they are extremely sensitive to sulfonylureas, which means as HNF1 alpha is also expressed in the liver, and it's important in the metabolism of sulfamides. And in this case, if you treat these people with this medication, you have a higher risk of hypoglycemia. And so to make the diagnostic of mutation HNF1 alpha, which is called MURD3, it may improve the way you treat this patient. You avoid the sulfonylureas, or at least you are very careful in the dosage of this treatment. Now, sometimes the analysis of very rare cases are extremely useful for research, and that is the case with neonatal diabetes. It's only 1 every 300,000 newborns. And, but it's a very severe condition, and people are treated with insulin for the first day of their life. And genetics in the last 3 or 4 years have made tremendous progress to understand the molecular basis of this form of diabetes. And again, that has some implication for diabetes research in general. What different groups have found, including my group, was the role of the 2 genes encoding for the potassium channel in the development of diabetes. I told you that glucokinase and glucose metabolism is the first event for the insulin secretion, but the second event is the closure of the potassium channel. And the closure of the potassium channel is responsible for calcium entering in the cell and then exocytosis of insulin. And when you have a mutation in the channel itself, named KIR6.2, or the regulatory element CR1, which is the receptor of sulfonylureas, you have a permanent opening, and then you don't have any secretion of insulin. So that has been found that a large proportion of this subject have mutation in one of these 2 genes. The consequence of that is important clinically. Now, it is possible to have a very, very good correlation between the nature of this mutation, the functional effect on this mutation, especially the sensibility to ATP, and the clinical severity of this disease.